Hey everyone, welcome to The Explainer. Today, we're taking a culinary masterpiece and, well, putting it right under the scientific microscope. If you've ever made a Semifreddo, you already know it's not just your standard ice cream. Oh no, it's actually a high-stakes thermodynamic balancing act. It's a literal exercise in molecular control. So let's dive in and explore the absolute physics of flavor together, shall we?
Okay, let's dive right into the fundamental mystery of this dish. Seriously, why doesn't a Semifreddo freeze completely solid? Think about it. If you take water, cream, and sugar, mix them all up, and throw them in a freezer at 0 degrees Fahrenheit, you should, by all laws of common sense, get a rock-hard block of ice. Right? But a perfect Semifreddo, it stays absolutely luscious. It yields to a fork. It practically melts the second it hits your palate. So how on earth does it avoid turning into a giant ice block?
To answer that, we're going to treat this like a strict scientific mission protocol, following 5 distinct phases. First, the half-cold physics. Second, matrix containment. Third, rapid nucleation. Fourth, tempering and the guillotine. And finally, troubleshooting.
All right, let's kick things off with Phase 1, the half-cold physics.
What's really, truly fascinating here is the literal chemical manipulation of water, sugar, and fat. Now, okay, don't panic when you look at this thermodynamics equation. The crucial point isn't to memorize the math, I promise. It's to understand what it actually represents. When you whip 240 Fahrenheit invert sugar syrup into an Italian meringue, you are dissolving a massive concentration of solutes into a solvent. That intensely high sugar concentration physically interrupts and prevents the water molecules from locking together into a rigid, solid ice lattice. Even at standard, super cold freezer temperatures, you are literally, chemically, lowering the temperature at which this mixture can freeze solid. How cool is that?
And, this brilliantly illustrates the 2 pillars of the dessert's half-cold state working perfectly together in harmony. On one side, we've got that high sugar content doing the heavy lifting of lowering the freezing point. And on the flip side, we have insulation. The millions of microscopic air bubbles that you whipped into the meringue act like tiny little thermal insulators. They are physically insulating the fat from the chocolate and the mascarpone, which keeps the texture super light on the palate even when the dessert is sub-zero. It's chemistry and physics working in perfect tandem.
Moving right along to Phase 2, matrix containment.
Now, if you want a Semifreddo that you can beautifully, perfectly slice, you cannot just pour this mixture into some random bowl. You really need strict hardware here, specifically an 8x4-inch metal loaf pan. Why metal? Well, because it conducts heat away from the dessert much faster than glass or silicone, which accelerates the freeze. But here is the absolute genius hack for your containment liner. You need to line this pan with plastic wrap. But let's be real, plastic wrap never behaves, right? It's a nightmare. So you lightly wipe the inside of the bare metal pan with a damp cloth first. When you lay down the plastic wrap, it will instantly cling to the wet metal, allowing you to smooth it out flawlessly.
And listen to me, you must smooth it out perfectly. Take a look at this quote from our source material, because honestly, it feels a bit like a threat. Any wrinkles in the plastic will permanently scar the surface of your Semifreddo. You've got to smooth that plastic out or your dessert is going to bear the physical consequences. It's going to look marred and unprofessional, and nobody wants that after putting in all this effort, right?
So, once your matrix is perfectly lined, you'll gently scrape in your folded chocolate meringue mixture. Then, and pay attention, because this is a very specific instruction, you tap the pan firmly on the counter exactly twice. Not once, not 5 times, exactly twice. This precise physical shock dislodges any massive hidden air voids that would totally ruin your slices later on. Finally, you take that 3-inch overhang of plastic wrap and fold it tightly over the top to seal the environment completely tight.
Okay, we're locked and loaded. Phase 3, rapid nucleation.
Now we enter the deep freeze. This is where the environmental temperature absolutely dictates your final texture. Rapid freezing is non-negotiable here, guys. You must place that sealed loaf pan in the absolute coldest part of your freezer. We're talking the very back, bottom shelf. Literally never put it in the freezer door because that fluctuates in temperature every single time you open it to grab some ice. And it must sit there, completely undisturbed, for a minimum of 8 to 12 hours.
So why are we being so militant about rapid freezing? Well, when you freeze the mixture rapidly, you force the water molecules to form thousands of microscopic ice crystals, and that is what gives you that incredibly smooth, luxurious mouthfeel. If you freeze it slowly, on the other hand, those molecules have time to coalesce into a few large, jagged ice crystals. And let me tell you, large ice crystals equal a crunchy, icy, completely ruined dessert.
Speed is absolutely everything here. All right, the stakes are getting higher. Phase 4, tempering and the heated guillotine. We've survived the freeze, but here is the slightly terrifying reality. If you attempt to slice 0-degree Fahrenheit cocoa butter with a cold knife, the chocolate matrix will fracture and literally shatter like glass. To prevent a total disaster, we must initiate thermal tempering. First, you unmold the dessert and carefully peel off that plastic wrap like a second skin. Then, you let the Semifreddo sit at room temperature for 10 to 15 minutes. You are waiting for a very, very specific visual cue. The surface will lose its frosty matte finish and gain a slight, beautiful sheen. That ambient room temperature is softening those rigid fats, the cocoa butter and the mascarpone, just enough to yield to a braid.
Once you see that sheen, it is time for the heated guillotine technique. You have to move deliberately here. Step 1, submerge a sharp, non-serrated chef's knife into a pitcher of boiling hot water for exactly 15 seconds to heat the steel. Step 2, and this is absolutely critical, wipe the blade completely dry with a kitchen towel. If you slice with a wet knife, that hot water will melt the sugar and leave hideous white streaks all over your beautiful chocolate matrix. Step 3, slice straight down. And step 4, you must clean, reheat, and thoroughly dry that blade between every single cut. No exceptions.
I really want to pause on this specific mandate. Slice straight down, do not saw. Let that sink in for a second. A sawing motion will snag those softened fats and drag them, completely tearing the structure apart. You are a guillotine. One clean, heated, vertical drop. That, my friends, is exactly how you preserve the integrity of the dessert.
Okay, everybody, take a breath. We made it to phase 5, troubleshooting, or as I like to call it, the autopsy.
The absolute best way to truly master a dish is to scientifically deconstruct its failures. So let's look at defect number 1. Your dessert feels like you're eating tiny shards of ice. The root cause? Condensation from a bad seal, or, way more likely, your freezer's auto-defrost cycle. You see, standard freezers slightly warm the chamber every so often just to prevent frost buildup. But that warming allows our beautiful microscopic ice crystals to melt slightly. And when the freezer cools down again, they refreeze into larger, jagged shards, a process known as Oswald ripening. The correction here is simple. Ensure an airtight seal and eat the dessert within 3 to 4 days before that auto-defrost cycle ruins it. Now, defect number 2, it's a melted puddle. The root cause here is tempering way too long for your specific ambient kitchen temperature.
And that brings us directly to this crucial number, 4. Because that 10 to 15 minute tempering window we talked about earlier, well, it is entirely dependent on your environment. If you are in a standard 70-degree kitchen, 10 minutes is perfect. But if you are in an 85-degree summer kitchen, 4 minutes might be the absolute maximum amount of time your dessert can sit out before the structural fat completely liquefies and the whole thing collapses. You really must watch closely for that sheen.
And there you have it. When you execute the protocol flawlessly, balancing that freezing point depression, perfectly managing rapid nucleation, and executing thermal tempering, you are left with a perfect, silken slice of Semifreddo. It really is a marvel of thermodynamics just hiding in plain sight on the dessert menu. I hope this explainer empowered you to see the actual science behind the sweetness. So I'll leave you with this question. What seemingly magical culinary phenomena should we scientifically deconstruct next? Let me know. Keep experimenting in your own kitchens, and I'll catch you next time.